This is the fourth video for section 8.5, where we're going to look at another example of partial fractions, or using partial fractions to find antiderivatives. So I'm going to do one of the examples that I mentioned in the last video that was a little bit different than just having straight linear factors. So if we take a look at this example and we factor the denominator, each term in the denominator has a common factor of x squared, so I can pull that out with a remaining factor of x plus 1. That means that what I have here is a repeated factor. Okay, I have a repeated factor of x times x. I know it's quadratic, but the difference is, so let me discuss that. So the difference is this versus this. So this right here is a repeated linear factor, and this is a quadratic factor. So in this case, the x is being squared, and so it is a repeated factor. So when I write out my partial fraction decomposition, I'll have a over x plus b over x squared plus c over x plus 1. Don't forget to set it equal to the original fraction. Let's get rid of the denominators, and so remember that that means multiplying the entire equation by that common denominator. And if I multiply this first term by that common denominator, one of the x's is going to cancel with one of the x's here, and I'm going to be left with a times x plus 1. And if I look at the second multiplication, both x squareds are going to cancel, so I'll have b times x plus 1. In the third, the x plus 1 is going to cancel, so I'll have c times x squared. And then if I look at the last multiplication, the entire denominator is going to cancel, giving me a 2. Let's distribute. Here I sort of have a couple of different things to distribute, but on the inside, x times x plus 1 is x squared plus x. So let's distribute a through that expression. Distribute b and distribute c. Okay. So notice that I have two quadratic terms, and I have two linear terms, and then I have one constant term. But over here, the only thing that I have is a constant. So if the quadratic term went away and the linear term went away, then that means that their coefficients must have been 0. So I can think of this as 0x squared plus 0x plus 2. Let me go ahead and combine my like terms here. So I've got ax squared plus cx squared. Those are my quadratics. And then my ax and my bx are linear. And then b is my constant. So from that I can set up 3 equations. I can also factor out my x terms So if I factor out an x squared, I have a plus c. And if I factor out an x, I have a plus b. So my three equations are that x squared times a plus c equals 0x squared. X times a plus b equals 0x. And then b equals 2, which is a really great equation to have. It's going to make our system of equation solving much easier. Let's go ahead and deduce a couple of things from these equations that we've written. If x squared times a plus c equals 0x squared, then we know that a plus c has to equal 0. Similarly here, a plus b also has to equal 0. So let's take that system, write it out, and solve it. Now I'm going to use some different methods to solve this particular system of equations, especially since I already know that b equals 2. So if I know that b equals 2, then I can plug that into this equation in the middle here and find out that a has to equal negative 2. And once I know that a equals negative 2, I can plug that into my first equation to get c, and I find out that c equals positive 2. So I've got a equaling negative 2, b equaling positive 2, and c equaling positive 2. Therefore, my fractions are negative 2 over x plus 2 over x squared plus 2 over x plus 1. And so what I want to do is integrate each of these individually and then add my results. The first one, I can take the negative 2 and I can think of it as a constant multiple, factor it out. And the result will be negative 2 natural log of absolute value of x. In the second one, what you might want to do here is think of this as, sorry, I lost my train of thought there for a second, is think of this as 2, if you want to pull that constant multiple out, times the antiderivative of x to the negative 2. This time we don't get a natural log. We can use a power rule there. And so if we add 1, we'll get negative 1, and then divide by negative 1 means we'll get negative 2 times x to the negative 1 power. And then in the last one, we'll get another natural log, 2 times the natural log of the absolute value of x plus 1. Alright, so a couple things that I'm going to do to simplify my terms here. First of all, I've got 2 natural log terms, and I can combine those. So you can think of them in the opposite order, where this one is positive and this one is negative, and so it's really this term subtract this term. So when I go to combine them into a single natural log, what I get is the x plus 1 squared, remember the squared coming from that constant multiple, which makes it a power, over x squared. Same idea here with the power coming up here. But because it's negative, it goes on the bottom. And then I also have plus a minus, which is just subtract. 2 times x to the negative 1, or 2 over x plus c. So that'd probably be a good way to write that answer.